Welcome to the deep dive. We all appreciate a system that just works instantly, reliably, whether it's the traffic light on the corner or the processor in your computer pulling data from a drive. But do you ever stop and wonder what the fundamental language of those devices even is? What lets a circuit make a decision in, like, nanoseconds? Well, today we are taking a shortcut right into the mathematical heart of all digital systems, combinational logic. Our mission is to really get into the source material you sent over and understand the core mechanics. And the main concept is, well, it's deceptively simple. A combinational circuit's output is determined only by its current inputs. It's completely memoryless. It doesn't care about what happened a millisecond ago. It just sees an input and boom, delivers an output.
That's it. And that independence from the past, from any historical state, is what makes them so incredibly fast and stable, which is, absolutely critical for modern computers. But before we can even talk about speed, we have to agree on the language. Every single digital system, when you get down to it, relies on Boolean variables. These variables, they can only be one of two things, a 0 or a 1, true or false. But what's really important for you to grasp is the physical side of this. In a real circuit, these zeros and ones are just specific voltage levels. A low voltage is a 0, a high voltage is a 1. And every tool we're about to explore, from the algebra to the maps, is all about manipulating that simple signal.
Okay, so let's unpack that language. We're starting with the math, right?
Yeah.
Boolean algebra. This is the tool we use to analyze and, more importantly, to simplify the expressions that describe what a logic circuit actually does. And the whole thing really just rests on three basic operations: AND, or OR, and NOT. NOT is sometimes called logic complement or inversion. These are really the simplest decisions a circuit can make.
Yeah, those are like the primary colors. But to build anything complex, we also lean really heavily on four other operations: NAND, NOR, exclusive or XR, and exclusive NOR XNOR. What's amazing is that with just those 7 operations, you can describe basically any logical relationship, no matter how complicated. And when we actually build these, we're talking about logic gates. They're just the physical circuits that perform these functions. But designers have all these little visual tricks to speed things up, like the bubble. That little circle you see on a circuit diagram, that just means logic inversion. It's shorthand, so you don't have to draw a whole separate NOT gate every time. In a big schematic, that saves a ton of space and confusion.
The clarity is everything. Speaking of clarity, we also have to get the difference between active high and active low signals. You see that everywhere.
Absolutely. Active high just means the function turns on when the voltage is high, a logic 1. Active low means it turns on when the voltage is low, a logic 0.
So why would a designer ever choose active low? Seems a bit counterintuitive.
It's often about noise immunity. Critical things like a system reset line are often active low because a low voltage is closer to ground. That makes it much less likely that some random electromagnetic noise could accidentally trigger a reset. It's, a design choice for robustness.
So we have the language, the symbols, the gates. But why all the focus on the algebra? We keep coming back to this idea of simplification.
Because simplification is what makes a product commercially viable. It's everything. These Boolean theorems, they exist for one reason: to make logic expressions simpler. And a simpler expression means you need fewer physical gates. That means a smaller chip, less power, lower cost, and this is the big one shorter propagation delay. It means a faster system.
And when we talk simplification, the real heavyweights are De Morgan's theorems.
Oh, they're essential. Forget the dense math for a second and just think about the idea behind them. De Morgan's theorems basically show this amazing duality between AND and OR. They let you swap the operators so you can turn a bunch of ANDs into ORs as long as you invert the inputs and the output. And that's a total game changer because you can then build a circuit using whichever gate is cheapest or most available. For example, the sources gave that simple expression: x plus x bar y. You apply some basic Boolean laws, and it just simplifies down to x plus y. That one algebraic step could eliminate multiple gates from your design instantly.
Okay, so now we're moving from the abstract math to the definitive map of a circuit's behavior, the truth table.
The truth table is the gold standard. It's a static list of every single possible input combination and what the output will be for each one. And the rule is, if you have n inputs, you need 2 to the n rows to cover every possibility. No exceptions. So if you have 5 inputs, that's 32 rows you have to account for.
And here's where it gets really powerful for a designer. You can actually work backwards. You don't have to start with an equation. You can just define how a circuit should behave in a truth table and then figure out the math from that. And that process is called deriving the sum of products form, or SOP. You just look at the rows where the output is a 1, You write out the input combination for that row as an A and D function, and then you just OR all of those terms together. That gives you your starting equation, and then you go back and simplify it.
Right, and that introduces some important jargon. Each of those product terms is called a min-term.
Yep.
And when you list all the min-terms that give you a one output, that's called a canonical form. So when you see a designer write something like F equals sigma M3 4 5 6 7, it's not meant to be cryptic. It's just shorthand. It's saying the output is 1 when the input combination matches row 3 or row 4 or row 5 and so on. It's a compact way to describe the whole table.
So the truth table is the static blueprint, the complete checklist. But circuits exist in time, which brings us to the dynamic view, the timing diagram.
Exactly. If the truth table is the blueprint, the timing diagram is the movie. It's a graph that shows the signal voltage levels over time. It's critical for showing us timing relationships. For instance, if input A changes now and input B changes a few nanoseconds later, the diagram shows you precisely when the output finally settles to its new value. This is literally what engineers look at on an oscilloscope or a logic analyzer. They're checking if the real circuit matches the theoretical timing diagram.
Okay, let's go back to simplification, because the incentives are just so high. You mentioned it improves speed by reducing propagation delay. That's the time it takes for a change at the input to actually cause a stable change at the output. But if the algebra is so powerful, why do we need another tool? Why bother with something visual like a K-map?
That is a great question. Because Boolean algebra gets really hard for our brains to handle with, say, 4 or more variables. It is just so easy to miss a simplification step. The Gardner map, or K-map, lets you bypass all that tedious algebra by turning the problem into a visual pattern recognition game. A K-map is basically a rearranged truth table. It's made of cells 4 for 2 variables, 8 for 3, 16 for 4, and the genius is in the layout. The cell numbers, the min-terms, they're intentionally not in sequential order. It uses something called gray code, which guarantees that any two cells next to each other, and that includes wrapping around the edges, differ by only a single variable changing. So if you see two ones next to each other, you know instantly you can eliminate a variable. No algebra needed.
It's like finding a common denominator just by looking at it. And for anyone diving into this, the rules for grouping are everything. You can't just circle randomly, right? There are 5 key rules. First, your group size has to be a power of 2, 2, 4, 8, etc. Second, you have to include all the ones. Can't leave any behind. Third, each group needs to be as big as you can possibly make it. Fourth, use the fewest number of groups possible to cover all the ones. And finally, groups can overlap if it helps you make a bigger group. It's all about optimization.
And sometimes the K-map gives you this massive advantage, this freebie called the don't care term. The don't care term, you'll see it as an X or a D, comes up when some input combinations are either impossible or just irrelevant for your circuit. A classic example is a circuit that handles BCD numbers binary coded decimal. BCD only uses the combinations for digits 0 through 9. The binary codes for 10 through 15 will never ever happen, so the output for those inputs doesn't matter. They are don't cares. So strategically, you can treat that X as either a 1 or a 0, whichever helps you make bigger groups. If turning an X into a 1 lets you make a huge group of 8, which eliminates 3 variables from your final equation, you do it. It's the ultimate lever for simplification.
So we've taken this complex behavior, used the K-map to distill it down to its simplest form. What does this all mean for actually building things at scale? It means efficiency. And that brings us to universal gates. The source is really clear on this. Any logic circuit you can dream up can be built using only NAND gates or only NOR gates, which is why they're called universal. The manufacturing benefit is just enormous. You only need to produce and stock one type of simple logic chip to build anything.
Exactly. And those simple gates get packaged into bigger, more useful blocks. We call them medium scale integration, or MSI blocks. And these are the real workhorses of digital design. First up, you have the decoder. It takes a binary code as an input and activates one unique output line. A common one is the 3 to 8 decoder. 3 input lines select one of 8 outputs. These are absolutely essential for things like memory addressing in a computer. It makes sure only the correct memory chip gets activated.
And the opposite of a decoder must be an encoder?
You got it. An encoder does the reverse. It takes a bunch of inputs, say 8, and converts an active input into a smaller binary code, like a 3-bit output. Then you get to the king of data routing, the multiplexer, or MUX. People call it a data selector. It's just an electronic switch. It takes data from many different input channels and routes one of them to a single output line. Think about a computer bus. The same set of wires might need to carry a memory address one moment and then instruction data the next. An MUX uses selection inputs to choose which channel gets to use the bus at that exact moment. It's all about sharing resources.
And naturally, because digital logic loves symmetry, there's a demultiplexer or DMUX.
Precisely. A DMUX does the opposite. It takes a single input line and routes it to one of many possible output lines, again, based on selection inputs. So a DMUX gathers data into one stream, and a DMUX distributes it back out. Together, they are just fundamental for managing information flow.
Wow. That was an essential deep dive. We've really covered the whole stack, from the foundational zeros and ones through the algebra, the truth tables, the timing diagrams, and then that critical shortcut, the K-map.
Yeah?
And we've seen how all that theory translates complex math into real, cost-effective hardware like a MUX or decoder.
And if we circle back to the big picture of engineering trade-offs, the goal we chased this whole time was simplification, for reliability, for speed. But we also hinted that if you simplify too much, you can sometimes run into trouble. So this leaves a really interesting question for you to think about. We know simpler circuits are faster, but sometimes they can create these tiny momentary glitches. We call them hazards. If a designer uses a K-map to get the absolute most minimal circuit possible, what kind of specific localized timing problems might that extreme simplification create? And how could that, potentially compromise the very reliability they were trying to achieve in the first place? That tension between minimum cost and maximum reliability, that's really the art of advanced digital design.